have, the more light we can see and the farther back we can view. So, we've learned in the last century that there are exotic objects in the universe, black holes. We've even learned that there's dark matter and dark energy that we can't see. So you're looking now at an actual image of dark matter. You got it. Not all audiences get that. So, the way we infer the presence of dark matter, we can't see it, but there's an unmistakable tug due to gravity. We now can look out, we see this sea of galaxies in a universe that's expanding. What I do myself is to measure the expansion of the universe, and one of the projects that I carried out in the 1990s used the Hubble Space Telescope to measure how fast the universe is expanding. We can now trace back to 14 billion years. We've learned over time that stars have individual histories. That is, they have births, they have middle ages, and some of them even have dramatic deaths. So the embers from those stars actually then forms the new stars that we see, most of which turn out to have planets going around them. And one of the really surprising results in the last 20 years has been the discovery of other planets going around other stars. These are called exoplanets. And until 1995, we didn't even know of the existence of any other planets other than going around our own sun. But now there are up almost 2,000 other planets orbiting other stars that we can now detect, measure masses for. There are 500 of those that are multiple planet systems. And there are 4,000, and still counting, other candidates for planets orbiting other stars. And they come in a bewildering variety of different kinds. There are Jupiter-like planets that are hot. There are other planets that are icy. There are water worlds, and there are rocky planets like the Earth, so-called super-Earths, and there's even been planets that have been speculated diamond worlds. So we know there's at least one planet, our own Earth, in which there is life. We've even found planets that are orbiting two stars. That's no longer the province of science fiction. So around our own planet, we know there's life. We've developed complex life. We now can question our own origins. And given all that we've discovered, the overwhelming numbers now suggest that there may be millions, perhaps, maybe even hundreds of millions of other stars that are close enough, just the right distance from their stars that they're orbiting, to have the existence of liquid water and maybe could potentially support life. So we marvel now at those odds, the overwhelming odds. And the amazing thing is that within the next decade, the GMT may be able to take spectra of the atmospheres of those planets and determine whether or not they have the potential for life. So what is the GMT project? It's an international project. It includes Australia, South Korea, and I'm happy to say, being here in Rio, that the newest partner in our telescope is Brazil. It also includes a number of institutions across the United States, including Harvard University, the Smithsonian and the Carnegie institutions, and the universities of Arizona, Chicago, Texas Austin, and Texas A&M University. It also involves Chile. So the making of the mirrors in this telescope is also fascinating in its own right. We take chunks of glass, melt them in a furnace that is itself rotating. This happens underneath the football stadium at the University of Arizona. It's tucked away under 52,000 seats. Nobody knows it's happening. And there's essentially a rotating cauldron. The mirrors are cast, and they're cooled very slowly, and then they're polished to an exquisite precision. And so if you think about the precision of these mirrors, the bumps on the mirror over the entire 27 feet amount to less than 1/1,000,000th of an inch. So can you visualize that? Oh. Human hair, that's 1/5,000th of the width of one of my hairs over this entire 27 feet. It's a spectacular achievement. It's what allows us to have the precision that we will have. So what does that precision buy us? So the GMT, if you can imagine, If I were to hold up a coin, which I just happen to have, and I look at the face of that coin, I can see from here the writing on the coin, I can see the face on that coin. My guess is that even in the front row, you can't see that. But if we were to turn the giant Magellan telescope, all 80 feet diameter that we see in this auditorium, and point it 200 miles away, if I were standing in Sao Paulo, we could resolve the face of this coin. That's the extraordinary resolution and power of this telescope. And if we were if an astronaut went up to the moon 250,000 miles away and lit a candle, a single candle, then we would be able to detect it using the GMT. Quite extraordinary. Here's an image. This is a simulated image of a cluster in a nearby galaxy. Nearby is astronomical, it's all relative. It's tens of millions of light years away. This is what this cluster would look like. So look at those 4 bright objects. And now let's compare it with a camera on the Hubble Space Telescope. You can see faint detail that starts to come through. And now